our 5-minute check over chapter 1. So looking at it, it says describe the end behavior of f of x, which is equal to 4x to the fourth plus 2x minus 8. This one, we could graph it, okay, and you would find that it's a parabola looking thing. Okay, it's a parabola, it has a little hump in it, but we're talking about end behavior. End behavior of these graphs is always going to be determined by this leading coefficient and the exponent that is of the leading coefficient. If it's even, both ends are going to go the same way. Okay, if it's odd, one's going to start low and then it's going to end high, or it's going to start high and end low. But since this is an even one, and since my a value is positive here, okay, I know that as x goes towards a negative infinity, f of x goes towards a positive infinity. And as x goes towards a positive infinity, f of x also goes to a positive infinity. So we're looking for that answer, and that should correspond to answer D. Okay, and that's part of the power functions. Okay, you should have also been able to pick that up off of polynomial functions. Okay, odd exponents for the leading coefficient, the ends go opposite, but when it's even, they go the same direction. So this one's like a U with a little hump. Both ends are in the air going towards positive infinity. So we're good that way. Okay, this one, identify the parent function of f of x of g of x, which is equal to 2 times the absolute value of x minus 3 plus 1. Describe how the graphs of g of x and f of x are related. So first, ask yourself, what's the parent function? Well, it's the absolute value of x. Okay, so that doesn't help us eliminate any answer choices. Okay, so now we have to look at the translations that are happening. Notice that we have a value of 2 where a should be. Okay, so this is your vertical dilation factor. That means this graph has been stretched by a factor of 2. Okay, so it's absolute value, it's stretched by a factor of 2 vertically, but then we have an inside transformation. And remember that this, since it's minus, that's going to move it 3 units to the right. And then this outside is your vertical translation factor of plus 1. So that's going to move it 1 unit up. Okay, so we're looking for one that says we're translated to the right, we're shifted 1 unit up, and we're expanded vertically. So that should be letter A. Okay, and that just comes from your transformations of polynomial functions. Here we go, a little bit of algebra. It says find f of g of x and g of f of x for f of x is equal to 2x minus 4 and g of x is equal to x squared. So composition of functions. Okay, we want to find f of g of x. So f g of x. Okay, so my f of x is 2x minus 4. My g of x is equal to x squared. Erase that one. If we're going to try to find f of g of x, remember we have to plug this whole term into the variable. I'm good, thank you. Into the variable here, okay, and then we carry out all of our order of operations. So that's 2 times x squared minus 4. So f of g of x is equal to 2x squared minus 4. Okay, working on the other side to find g of f of x. Okay, once again, we have to plug this whole term, all of f of x, into this equation, and we have to carry out our other order of operations. So that is 2x minus 4 squared. Okay, so then we'd have to carry it out using FOIL. So 2x minus 4 times 2x minus 4. That leaves to you 4x squared minus 8x minus 8x plus 16. which gives you 4x squared minus 16x plus 16. So those are our two answers. This is g of f of x and f of g of x. So looking at our answer choices here, just trying to find the one that maps to it. It looks like it is going to be answer C. Bang. And our last one, evaluate f of 2 of x, f of 2x if f of x is equal to x squared plus 5x plus 7. So function notation here. Remember, we have to plug it in. Whatever is our independent variable, we have to plug it in for each occurrence of x to find our dependent variable. So f of 2x is equal to 2x squared, quantity of 2x squared, plus 5 times the quantity of 2x, plus our constant of 7. Carry out order of operations. 2 squared is 4, x squared is x squared. So 4x squared plus 10x plus 7. We'd look to determine if there's any areas that we can combine. Looking at this one, that is not the case. So our answer is 4x squared plus 10x plus 7, which also corresponds to letter C. Okay, so we've analyzed parent functions and their families. Okay, we did that in lesson 1.5. Today we're going to graph and analyze power functions. Okay, and we're going to graph and analyze radical functions and solve radical equations. Okay, should be a fun one. Like I said, we're also going to do what's called a power regression. That's honestly going to be the hardest one because it has multiple steps. It requires you to use your graphing calculator or the updated version of that graphing calculator app in order to complete it. Here's your new vocabulary. We have power function. We have monomial function. We have radical function. And we have extraneous solution. Okay. So a power function. A power function is any function that can be written f of x, which is equal to ax to the n, where a and n are constants. Okay, so everything's going to have an exponent. Okay, it's not an exponential function where x is the exponent. We have two constants, a and a constant n. Okay, a, once again, it's your dilation factor. Okay, n is going to determine whether it's odd or even, and that's by whether n is odd or even. Okay, a monomial function. Power functions are a type of monomial functions. Okay, so monomial is kind of the umbrella. It's any function that can be written as f of x, which is equal to a, or f of x, which is equal to a times x to the n. Okay, so monomial is the umbrella. Power function falls underneath monomial functions. Okay, and we're dealing with single terms. So if you think of the difference between poly and mono, here, mono means single. So we're dealing with singular terms, whereas with polynomial functions, we were dealing with multiple terms. Okay, radical function. So radical functions can be given to you in two different forms. They are typically, okay, right there, where f of x is equal to the nth root of a to the x. Okay, understand that this is equivalent to ax to the 1 over n. So some of our power functions, if n is a fraction, it's really a radical equation, a radical function. Okay, and that comes from your properties of rational exponents. Okay. That's something that we did very, very early, being able to manipulate them and being able to solve the radicals. And then extraneous solution, that is a solution that's really not a true solution. Because when we're solving these radical equations, we're going to be applying powers. Okay, the only way that you can get rid of a square root is to square it. What that allows is you get a positive and a negative answer. An extraneous solution would be when one of those don't truly solve the equation. Okay, but you can get to it algebraically. But it's not a true solution. It's extra. It's extra, extra, extra. All right. Here's probably the most important thing of the section. Okay, these 4 quadrants right here. So first, remember we're dealing with f of x is equal to ax to the n. So it's talking about the exponent. Okay, at the top, n is even. Okay, n is even. And this will be true for every single power function. If n is even and a is positive, it is going to have these characteristics. The domain from negative infinity to a positive infinity. The range from 0 to a positive infinity, because it doesn't cross the x-axis. Once again, n is even, a is positive. So our parabola is facing up. We don't have horizontal translation factors. Okay, we don't have vertical translation factors. We are just dealing with the leading term. Okay, the continuity, or x and y intercept, are both 0. The continuity of each function is continuous for x for all real numbers. Symmetry is y-axis. The minimum, 0, 0. That's your extremal point right there. It's decreasing from a negative infinity to 0 and increasing from 0 to a positive infinity. Because as we go from left to right, our graph goes down, and then it begins to increase as soon as we hit our extremal point. In behavior, the limit as f of x approaches negative infinity, f of x equals positive infinity. And the limit as x approaches positive infinity, f of x also approaches positive infinity. Okay, and once again, this is true for all power functions where n is even and a is positive. Okay, on the flip side, if n is even and a is negative, most of these things are going to stay the same. Like the domain, going to stay the same. X and y intercepts, both still going to be 0. We don't adjust anything for continuity. Symmetry is always going to be y-axis, okay? But here is where you get your first difference when you're talking about increasing and decreasing. So as you move from left to right, our graph is increasing, and then it hits 0, our extremal point, and then it's decreasing. Oh, didn't want to click off that slide. Okay, the end behavior is just flipped. Instead of approaching a positive infinity, like we do when n is even and a is positive, when n is even and a is negative, we approach a negative infinity. Okay, you'll also find that instead of having a minimum, we have a maximum. Okay, that's because this extremal point is the highest point in relation to everything else. It could be called the absolute maximum or the absolute minimum for an ax squared. Okay, you'll also notice that the range has flipped. Instead of 0 to a positive infinity, it's negative infinity to 0. Once again, we don't cross the x-axis. Okay, but once again, this is going to be true for each and every power function where n is even and a is negative. Okay, these two things are clutch because a lot of your questions ask you to analyze these graphs. If you can remember this stuff, you're going to fly through this assignment. Okay, and you don't really even have to graph it because you can pick that up off of the equation. So now let's look at when n is odd. So once again, it starts low and ends high when a is positive. So the domain and range still all real numbers from negative infinity to positive infinity. X and Y intercept still at the origin of 0, 0. It's continuous throughout its entire existence from negative infinity to positive infinity. It has symmetry that is based upon the origin. Okay, so that means if we were to rotate it 180 degrees about the point 0, 0, we would map on top of each other. Okay, it's point symmetry. No extrema. Okay, no extrema. It's going to be increasing from negative infinity to positive infinity. And the end behavior as the limit of f of x approaches, the limit as x approaches negative infinity, f of x approaches negative infinity. And the limit as x approaches positive infinity, f of x approaches positive infinity. Okay, and the same thing that you had when n was even and negative, a lot of these characteristics stay the same. Okay, the domain and range isn't going to change. Still from a negative infinity to a positive infinity. There's no cutoff. There's no values that we can't put in. X and Y intercepts at 0, 0. Okay. Continuity, continuous for all real numbers. Okay. There's no breaks in the graph. Symmetry, origin again. If we rotated 180 degrees, we would fall upon the graph. Still no extrema. Instead of increasing, we are decreasing throughout the entirety of the graph. So as we move from left to right across our graph continues to go down. And then the end behavior is switched. So the limit as x approaches negative infinity, f of x approaches positive infinity. And the limit as x approaches positive infinity, f of x approaches negative infinity. Okay, this is a crucial part. So I'm going to give you like a minute or two to write that down. Okay, off to rational or radical functions. Okay, once again, radical functions can be expressed as f of x is equal to x as the 1 over n, or 1 over n. That comes from your powers of rational exponents. Okay, so some of our graphs, even though they're power functions, they're going to end up looking like this. So if n is even, the domain and range, 0 to a positive infinity. Okay, so this is when n is even. This is like taking the square root, the fourth root, the sixth root, the eighth root, the 10th root. Okay, x and y intercept is at 0. Continuous on the interval from 0 to a positive infinity. That's because we can't take an even degree, or we can't take an even root of an odd number, because we can't get it. It's an imaginary number. Symmetry, there is no symmetry. Okay, it's increasing throughout the entirety of the graph. It looks like it's going to level out, but it really doesn't. The extrema, absolute minimum at 0, 0. Okay, that's that point right there, because everything else is higher than it. And then in behavior, the limit as x approaches positive infinity, f of x approaches positive infinity. Okay, it's increasing throughout its entire domain, even though it kind of appears that it levels off. Okay, so when n is odd, this is like taking the cube root, the fifth root, the seventh root, or the ninth root. It allows you to have negative values, okay, because negative 3 cubed is negative 27. So our domain and range from negative infinity to positive infinity. Okay, x and y intercepts still at 0. Okay, continuity, continuous over its entire existence. Symmetry is based upon the origin, because if we were to rotate it 180 degrees around 0, 0, we would map onto ourselves. It's increasing from negative infinity to positive infinity. There is no extrema. The end behavior, the limit as x approaches negative infinity, f of x approaches negative infinity, and the limit as x approaches positive infinity, f of x approaches positive infinity. Okay, I'll give you a minute to copy that down. Because once again, if you can make yourself fast looking at these and be able to identify it, it makes it pretty simple. The only time that these change is when we're dealing with negative exponents. Because negative exponents are no fun. All right, let's get into it and let's start using these things. So analyzing monomial functions. Describe the domain, range, intercepts, and end behavior continuity where the function is increasing or decreasing. So ask yourself, what's the value of A and what is the value of N? So on this specific graph, our value of A is 1/2 and it's positive. Okay, and our value of N is 6, so that's even. So that means it's going to have all the characteristics of a power function where A is positive and N is even. So the domain, all real numbers. The range is going to be cut off at 0 and it's going to go up. Okay, so from 0 to a positive infinity. The intercepts, crossing at the origin, 0, 0. The end behavior, as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches positive infinity. Continuity, it's going to be continuous throughout the entirety of the graph. Okay, and then where the function is increasing or decreasing, once again, this is that U shape, okay, with an extrema point at 0, 0. So it's going to be decreasing from a negative infinity to 0, and then it's going to be increasing from a 0 to a positive infinity. Okay, so in other words, it has all of these properties right here because it fits this form. It's guaranteed 100% to have those properties. It has to. Okay, they plug it in and they graph it. I'd like us to get, we could graph it if we wanted to. So if I were to plug it into Desmos, it's 1/2 x to the 6th, 1/2 x to the 6th. Oh. X. That's what it looks like when we graph it. And we can answer all these questions off of the graph, right? Domain, continuous, negative infinity to positive infinity, in behavior. As x goes towards a negative infinity, f of x goes towards a positive infinity, x towards a positive infinity, f of x towards a positive infinity. It's decreasing from negative infinity to 0 and increasing from 0 to a positive infinity. Okay, you can see all of that from the graph. And you might have to graph a lot of these just to get comfortable with them. But like I said, this section in this top left here, they have to be true for each and every power function. So if you can familiarize with these, okay, this section is cake. You can familiarize with these. Once again, the section is cake. Because you can answer all of these questions without ever having to graph it without ever having to plug in and create a table. But until you're getting comfortable with it, you're probably going to have to graph them a couple times until you see the patterns. So the domain, negative infinity to positive infinity, range 0 to a positive infinity. Once again, it comes down, touches the x-axis, and goes back up. Its intercept is at 0 for both x and y. Its end behavior is x goes towards a negative infinity, f of x towards a positive infinity, x towards a positive infinity, f of x towards a positive infinity. Continuity, they'll always be continuous, our power functions, throughout their entire domain. Decreasing from a negative infinity to 0, increasing from 0 to a positive infinity. Okay, and that would be your answer. And there's a picture of the graph again. So again, you can graph them and get it, but if you can familiar yourself with that, you're going to be fine. So here we have f of x is equal to a negative x to the fifth. So once again, our a value is negative. It's a negative 1 right there. Our degree is odd. Okay, domain and range going to be all real numbers. It's going to start high, end low. Okay, the intercept's going to be 0, 0 again. Has to have all of those properties. In behavior, since it starts high and end low, like this, since it fits this, it has to have all those properties. So as x goes towards a negative infinity, f of x is a positive infinity. And as x goes towards a positive infinity, f of x is a negative infinity. Okay, where the function is increasing or decreasing, it's decreasing for the entire graph. So your domain from a negative infinity to a positive infinity. The range from a negative infinity to a positive infinity, all real numbers. Intercept at 0, 0. In behavior, as x goes towards negative infinity, f of x is a positive infinity. And as x goes towards positive infinity, f of x is a negative infinity. That's because it starts high, ends low. It's continuous for all real numbers. It's decreasing on the interval from negative infinity to a positive infinity. So that's what your answer would be. They're asking you to analyze and come up with these general characteristics. Okay, and repetition, repetition, repetition. That way you can come up with these very quick, very easy. And like I said, you'll get to a point where you don't even have to graph it, because all of them share the same characteristics if you can recognize the pattern. But until you can recognize the pattern, there's no shame in graphing them. Okay, so describe where the graph of the function f of x equals 2x to the fourth is increasing or decreasing. So a is positive, n is even. Okay, so our U shape, right? And it's pointing up. It's going to be decreasing from a negative infinity to 0 and increasing from 0 to a positive infinity. Okay, and just finding those general characteristics. I can't tell you how long it took me to get to be able to figure it out. I think probably right about the back half of Algebra 2. But I had a great math teacher in Mr. Hemphill, but he repped them. He repped them. He beat them into our head pretty much. Okay, here's where it gets a little tricky. Functions with a negative exponent. So graph and analyze f of x, which is equal to the 2x to the negative fourth. From your properties, okay, anytime you have a negative exponent, it's really a reciprocal. It's really a reciprocal function. Okay, so if f of x is equal to 2x to the negative fourth, this is equivalent to 2 times 1 over x to the fourth, or 2 over x to the fourth. The negative exponent brings whatever term it's associated with to the denominator. So what does this give you? One, it's going to break up the domain. It has to. Okay, it's going to break up the domain because we're going to be undefined when x is equal to 0. So we're going to have an infinite discontinuity at some level. Okay, and looking at this graph, typing it into Desmos real quick, I'll get you there. So looking at this graph here, you can see we're undefined. We're undefined at 0. Okay, some of the characteristics of this. As x goes towards negative infinity, f of x approaches 0. Okay, that'll be consistent with almost all of our power functions with negative exponents. Doesn't matter if it's even or odd. This shape here, where they're both over the y-axis or the x-axis, is because our exponent was even. If it was odd, it would look like a true reciprocal function. Okay, your range has to be greater than 0. Okay, your domain, all real numbers except for 0. Increasing or decreasing, it's increasing from a negative infinity to 0, and then it's decreasing from 0 to a positive infinity. In behavior, once again, on this side, as x goes towards a negative infinity, f of x approaches 0. And as x goes towards a positive infinity, f of x approaches 0. Characteristics that'll be similar for each. Okay, continuity. It has an infinite discontinuity at 0. Okay, and that's just because of the nature of the negative exponent. Negative exponent throws the variable in the denominator, which allows it to become undefined. So the domain, like I said, can't be 0. Range from 0 to a positive infinity. We picked that up off the graph. Intercept, there is no intercept. We can't equal 0. We never touch x is equal to 0. Okay, so we can't have a y-intercept and our x-intercept. We never truly touch 0. We get very close, but we don't touch it. In behavior, as x goes towards a negative infinity, f of x is equal to 0. And as x goes towards a positive infinity, f of x is equal to 0. Continuity, infinite discontinuity at 0. That's because when we plug in 0 for x, it's undefined. Increasing from negative infinity to 0, it's decreasing from 0 to a positive infinity. Okay? That's what your graph looks like. These characteristics, though, same way that it did for a positive even function. Okay, these characteristics are going to be very, very similar for every time we have a negative exponent that is even. These characteristics don't change. So I'll give you a second to write those down. Give you a little cheat sheet to make it easy on you. Okay, off to the next one. Here we have graph and analyze f of x, which is equal to 2x to the negative third. Once again, this can be rewritten as 2 divided by x to the third. So if I plug it into Desmos, this is going to look more like a regular reciprocal function. Okay? Looking at increasing and decreasing, we're decreasing for the entirety of the graph. Okay, as we move left, our graph keeps going, goes down. I don't like how Desmos looks like it hugs the x-axis. It's not really doing that. Okay, it's decreasing. If I zoom way in, Well, that didn't help. It's decreasing from negative infinity to positive infinity. Okay, over the entirety of the graph. Decreasing, 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 decreasing. It looks that way because you're decreasing by thousands and millions as you're going from left to right. Talking about the range and domain, okay, your domain, x can equal 0. All real numbers except x can equal 0. Your range, once again, all real numbers, but we won't have a 0. Okay, in behavior, as x goes towards a negative infinity, f of x approaches 0. As x goes towards a positive infinity, f of x approaches 0. Okay, continuity, infinite discontinuity at x equals 0. Okay, once again, all these characteristics are going to stay the same. Okay, these will be the same for a negative exponent. The thing you got to worry about is if your a value is negative. Okay, but because then it'll change increasing and decreasing. So domain, all real numbers except for x can equal 0. Range, all real numbers, y can equal 0. There is no intercept. We get very close to touching 0, but we never will. In behavior, as x goes towards a negative infinity, f of x approaches 0. As x goes towards a positive infinity, f of x approaches 0. Those won't change. These things will never change here for your negative exponents that are odd. Continuity, infinite discontinuity at x equals 0, once again, won't change. Decreasing from negative infinity to 0 and from 0 to a positive infinity. They break it at the range or using the domain. If you were to put that it's decreasing for all real numbers, that I would accept that. Because you're basically saying the same thing, it's just broken at the undefined point. Okay, this would be the only thing. This would probably be the only thing that's flipped with a negative a value. Once again, we can pick all these things up from a graph, but if we can get good at it, we can find them very quickly, very easily. So, describe the end behavior of the graph of f of x, which is equal to 3x to the negative fifth. That's 3 divided by x to the fifth. So they both approach 0. That stays consistent. So as x goes towards a negative infinity, f of x is equal to 0. And as x goes towards a positive infinity, f of x approaches 0. So it's going to be answer D. It's again because the characteristics of the graph do not change. Okay, rational exponents. These fall under radical exponents. This could be rewritten as the fourth root of x to the fifth. Okay, so it's going to follow your radical exponents guide of those key concepts, those characteristics. The domain and range is going to be cut off. Okay, it starts at 0, 0, and then it kind of peers off into quadrant 1. Its intercepts, x at 0, y at 0. In behavior, as x approaches positive infinity, f of x approaches positive infinity. Continuity, continuous, as long as x is greater than 0. Where the function is increasing or decreasing, it's increasing over the entirety of the graph. In behavior, continuity. My tongue is tired. I've talked a lot already. Okay, and there's the way that your graph looks. Okay, once again, your rational exponents, they turn them into radical functions. Okay, so rational exponents, whenever we have an exponent that is a fraction, it is what I'm saying is that whenever we're given f of x is equal to x to the a over b, and I'm just plugging in variables, this is equivalent Okay, those two things are equivalent. So even though it's a power function, it's a monomial function, because we have ax to the n, it's really a radical function. Okay, so that was that second key concept. And the only difference is if b is even or b is odd. Okay, that's what determines the characteristics. We're not going to look at that one. That's because we got to talk about a power regression. Okay. Power regressions. Okay. So to create a scatter plot is just dots on an XY plane. Okay. In order to get your calculator to do this, the way that you're going to be given it is you're going to be given a table that looks similar to this. Okay. The hard part is we got to depend on find the dependent variable versus the independent variable. That's going to come from the question. So it says the following data represent the body length, L in centimeters, and the mass in kilograms of several African golden cats being studied by scientists. Okay, create a scatter plot of the data. So what this is, it's determining, hey, if you have this body length, typically you have this mass. Okay, so length is the independent variable, mass is the dependent variable. Okay, to get your calculator to do this, or to use this on calculator or on the phone, the steps are the same. First thing that you're going to click is you're going to click Stat, and then you're going to click Edit. Okay, then you're going to see a series of tables. They're broken down. It has L1, and it has a line L2, has a line L3, has a line L4. Okay, these are areas where we can input information. To simplify it, I only want you to use L1 and L2. So you're going to have to clear out some data and re-enter it back and forth. Okay, but for the simplicity of the instructions, L1, L2. Okay, we enter the independent variable. Wow, that good thing Ms. Klump didn't see that. Into L1. We input the independent variable into L1. We enter the dependent variable. Into L2. Okay. At this point, we can create the scatter plot by going to, we have to go to stat plot. Which is accessed by hitting second y equals. Okay, and make sure that it's turned on. Okay, at this point, then you can click graph and adjust your window. Okay, what that'll do in adjusting the window is make sure that your X values encompass all of what you entered into L1. Make sure your Y values encompass everything that you've entered into L2. Okay? And what that'll do is it'll give you a graph with all of these little different dots. Okay? And they're just going to be kind of spaced out, looking like they're at random, but they'll have some kind of a trend to them. Okay, those steps lead you to this. I always post the Zoom session, Rosalind. It'll be posted underneath the lecture. Okay, so doing those steps leads you to this. This is what your graphing calculator will look like, or your phone will look like. Okay, and you can see how they've adjusted the scale. This is what's known as a scatter plot. But we have to enter them into L1 and L2. Okay, that's step one of a power regression. That's to create the scatter plot. Okay, here we're given the same information, but they want us to determine a power function to model the data. Okay, what we need to do is after we've entered all of this information, okay, after we've entered this, to use the power regression, we click on Stat, we go to Calc, and we enter PWR. Or we'll find, after we hit Calc, there'll be an option for PWR regression. PWR REG, Power Reg. Okay, I think on the TI-83, it's like selection 11. Okay, on the calculator app, it actually says Power Regression. Okay, what that'll give to you is an equation. It'll actually give you the equation, but the way that it presents it to you is a little different. Okay, the Power Reg tool, that's the way that it's expressed on the TI-83. Okay, it's going to give you this, but the format at which it's going to give it to you is a little bit funky. And it's because you have to remember that power functions fit this form, a times x to the n. Okay, they always fit this form. The way the graphing calculator gives you that is it's going to say a. And then it's going to give you, in this situation, it would give you 0.018. And it's going to give you n. And in this situation, it's going to be 1.538. Okay? Once it gives you this, write it. Write it down in this format. Okay? In this ax to the n format. It gives you the a value. It gives you the n value. You have to rewrite it as 0.018 x to the 1.538. Okay? And that's giving you a function that models the data. Okay, it's giving you a function that models the data, but you have to write it down. Okay, you absolutely have to write it down, because on the next step, they're going to ask you to find a value that's not contained in the data given. Okay? So there's our power function. 0.018 m to the 1.538, or independent or dependent variable towards our independent variable. Okay, here's the step 3 part. Use the data to predict the mass of the African golden cat with a length of 77 centimeters. This is where you can use your graphing calculator, or you can use Desmos. Okay, but the key is we have to have this equation to be able to use these. Okay, the way that we would do this using the graphing calculator Okay, graphing calculator. Gotta quit sharing my screen. And then I'll be able to show you how to do it on desktops. Graphing calculator, we want to enter the power function into Y1, which is accessed by clicking the button Y equals. Okay, then we're going to hit then we're going to click graph, blah blah blah, click graph. Okay, make sure your window is still adjusted. Now we encompass all of the information for our X values, all of the information for our Y values. Okay, we're going to click graph. And then we're going to click trace. And then we would enter whatever number they're asking us to find. So in this case, it's 77. So since they want us to find 77 centimeters, after we click trace, we would hit trace, type in 77, click enter. What that does is it gets you the graphing calculator to plug 77 in and then spit out an answer. You can do this algebraically. Okay? Can do this algebraically using the calculator. Just understand it's a little bit more process. You would have to plug 77 in for L and then be able to solve it. So on their equation, they actually have it backwards. It should be M is equal to 0.18 L, 0.018 L to the 1.538. So you take 77 to the 1.538, times it by 0.018, and you would get your mass. Okay, you could do that algebraically by plugging it in. Graphing calculator makes it much easier because you can use the trace function after you have entered the power function into Y1. Okay? And once again, that's how you enter in graphs. We're going to do this Desmos-wise. Okay? You would enter the equation. So it was 0.018 x to the 1.538. Make sure that's right. Perfect. Take me back here. Okay, Desmos makes this a little tougher because we have to estimate. So click on your graph, drag until we hit 77. (77) 1.4345. Okay, that's the value that they're looking for. 1.4345. Trace would give you that same number, and so would solving it algebraically. Okay, and remember it's an approximation. I think they say it's 14.1. Okay, as long as we're within a couple decimal points, we'll be okay. The hard part is the power regression because it has a ton of steps. I know it's kind of a crash course. I wish I had the technology and being able to do that to walk you through it. But if you follow those steps, you're going to be okay. You're going to be okay. Use your resources available to you. If you need help with power regressions, send me an email. There's a bunch of YouTube videos out there on how to do a power regression. Okay, all of the information doesn't change. I'm indifferent if you get it from me or somebody else. So here, this would require us to do a power regression again. So looking at this, we would enter R into L1. We would enter F of R into L2. Okay, and then we would click, and we do that by clicking on Stat, Edit, enter L1, enter L2. Okay, then we'd click Stat again. We'd go to Calc, and we'd go to power regression. And then remember, it's going to give it to you in the form as A is equal to this, N is equal to this. Okay, and then it's our job to actually write the equation. This is your A value, this 5.9 on the first term. This is your N value. Okay, and what we get as a power regression on this one is we would get 5.2 for our A value, our N value as 2.9. Last thing, because I still got 10 minutes. Haha. Solving radical equations. Here we go. Algebraic nightmare. To put it in delicate terms, we'll say. Delicate terms. So we're given 2x is equal to the square root 28x plus 29 minus 3. Okay. So the first thing, I'm just going to do it off the slides. Okay, the first thing that we want to do is we want to isolate this radical. Okay, so we want to bring this minus 3 to this side so that we just have the radical by itself here. Okay, so step one, we isolate the radical. So they added 3 to both sides. They're left with 2x plus 3 on one side and the square root of 28x plus 29 on the other side. At this point, they square both sides to remove the radical. So they square it, okay? Once you take the square root of something squared, it's just left. That's why it's just 28x plus 29. On this side, they FOILed it out. 2x times 2x gives you 4x squared. 2x times 3 gives you 4x, or it gives you 6x. 3 times 2x gives you another 6x. 3 times 3 is 9. They combine like terms to get 4x squared plus 12x plus 9 is equal to 28x plus 29. Okay? Then they want to move everything from this side over to this side. So they subtracted 28x and they got negative 16x. They subtracted 29 from both sides and they're left with a negative 20. Okay, they want to get it to this form because here we have multiple options on how we can solve it. This is just a quadratic. We could use the quadratic formula. Okay, but this one is factorable. If we really wanted to, we could use a quadratic formula. Have that in your back pocket as well. But since this one's factorable, the first thing that they're going to do is they're going to factor out the greatest common factor of 4 from each one of these terms. So we're going to be left with x squared, 4x, minus 5, or negative 4x. So they factor that portion out. Okay, so now we're left with 4 times the quantity of x squared minus 4x minus 5. And then once again, we're going to factor this trinomial. So we're looking for 2 terms that multiply to equal a negative 5x squared that add up to equal a negative 4x. So that is x plus 1, x minus 5. Okay, factoring this trinomial. X plus 1, x minus 5. Okay, the zero product property states that since this is all equivalent to 0, one of these terms or both of these terms have to be set equal to 0. So we're going to set each one of them individually to 0 and we're going to solve it. So x minus 5 equal to 0, that's going to solve to be x equals 5. X plus 1 set equal to 0, solving for x is going to come to an x minus 1. Okay, that's the zero product property. And then they solve for x. So they'd add 5 on this one to get x is 5. They'd subtract 1 on this side to get x is equal to a negative 1. And we're left with our answers. Okay, to determine if we have extraneous solutions, because we had to square, what we need to do is we have to plug both of these back into the equation. Okay? So we have our original equation. We plug it in. So this is where they're plugging in 5. So 2 times 5 is equal to 10. 28 times 5 is 140. 140 plus 29 is 169. So that's going to be 10 is equal to 13, because the square root of 69 is 13 minus 3. So 5 is going to check out. Square root of 169 is 13 minus 3 gives you 10. They plug in -1. So 2 times -1 is -2. Negative 28 plus 29 minus 3. Square root of 1 is 1. So both of these check out. Neither one of these are extraneous. You will know if you have an extraneous solution because these will not balance out. Okay, that's the definition of them being extraneous. All right. The good news is problems like this are not on your homework, but there is one on the mastery check. Okay, so make sure you're flipping through these slides. I know I didn't get to go through it algebraically. It's because it would probably, to really walk through the steps and do them really well, I just didn't have enough time. But it's just using your order of operations. Okay, off to your homework.